Alrighty, gang, welcome back. This is our second day of Calc 2. And I'm sure at this point everybody knows where they are, but just in case it's your first day in class, this is MAC2312, section 004. It's John file sticker, Professor file sticker. And today we're going to kind of continue with our little introduction portion of the class. Last time, we reviewed use substitution. We reviewed how to use basic little substitution to solve integrals, both definite integrals and indefinite integrals. Today, we're going to move on and talk about areas between curves and this concept of called average value, a concept from statistics. Let me get my document camera configured, and we can begin. That camera, that resolution. There we go. All right, here we are. So, as always, this is MAC 2312, section 004, which is Calc 2. And the date today is the 7th of January, 2022. Today we're going to cover two sections, one of which is a review section, 6.1. It's a section on areas between curves. And this is supposed to be taught in Calc 1. But like use substitution or the substitution rule, it's something I'm not 100% confident is always taught as well as it should be in Calc 1, so I want to spend just a little bit of time going back over it. The other thing we're going to do today is talk about section 6.5, which is on the average value of a function. And this 6.5 average value is an important concept for anybody who's doing any sort of statistical analysis. When you kind of deal with probability mass functions, this concept of average value becomes very important. But we're going to start with 6.1, areas between curves. And again, I'm going to do it kind of quickly because it's something you should have seen in Calc 1, but just in case you didn't. A quick reminder, anybody who's, well, let me just ask, is anybody in the class for the first time today? Did anybody add between Wednesday and today? You can give me like a little thumbs up, react, or anything in Zoom to let me know if that's the case. Okay, so nobody who wasn't here on Wednesday. That's good. That means we can just move forwards. All right. Areas between curves. What are we doing with this stuff? The basic idea is that you can extend the concept of the definite integral measuring the area bounded by one function to measuring the area bounded between two curves. The simplest form of this is where both curves look how you expect a curve to look like y is a function of x. So I can draw one of them here in purple. I'll call this purple function f. And I can draw another one here in blue. I'll call this blue function g. Now, if you give me an interval from a to b, between these two curves lies a region. And the area we're hoping to calculate is the area of that region between the two curves. So this shaded area is what I would like to find. I'm so sorry, I'm getting a phone call here. It looks like it's coming from the campus number. Sorry about that. That was one of my colleagues. I'm not sure what she wanted to talk about, but I'll call her back later. So the idea here is that I want to find the area of this black shaded region that is between the purple curve and the blue curve. We know if we were to integrate just the function f from a to b, that would give me the area bounded between f and the x-axis. And we know if we were to integrate g from a to b, that would give me the area bounded by g and the x-axis, with anything below the x-axis being measured as negative. So if you were to take the area under f and then subtract the area under g, that would give you the area between the two curves. And you might want to think a little bit carefully about what happens down here, where the area under g would be measured as negative. But if you were to subtract that negative area, that's the same as adding that area, right? Subtracting a negative is the same as adding a positive. So the area between these curves, between f and g, from x equals a to x equals b, is going to be the integral from a to b of f of x dx, that's the area under f, minus the integral from a to b of g of x dx. And then using the properties of the definite integral, I can combine these into one integral. That's the integral from a to b of f of x minus g of x dx, right? Just like you can split an integral like this up into two, you can combine two integrals like these into one. And the way people normally think of this is as the upper function minus the lower function. And that will work regardless of whether one or both of those functions are positive, one or both of those functions are negative, or some of them are positive some of the time and some of them are negative some of the time. This upper minus lower scheme will work great as long as both of your curves are functions of x, right? As long as both of these curves pass the vertical line test, you are good to use this rule. A nice simple example, I might find the area between the constant function f of x equals 5 and the function g of x equals e to the negative x from x equals 0 to x equals 3. I'll tell you now, the real reason we're covering this section in Calc 2, one of them is that I want to review the material from Calc 1. That's at the very end because it's not always done well. That's true. The real reason, though, is that I want you to get practice drawing graphs. Okay, I know that especially over the pandemic, it's been a little bit loose. There's been a lot of online stuff, less on paper stuff, and our graphing skills have probably slipped a little bit. So it is all important that as you solve the homework problems, you draw the graphs by hand on your own, or at least attempt to do that. And then if you get stuck, use a graphing utility or something. But please do not just guess on the graphs in WebAssign until you get it right. That is a total waste of time. Totally defeats the whole purpose of doing the homework. So as you solve these problems, practice drawing the graphs by hand. If you get stuck on something, that's okay. I can help you. You can use Desmos if you get stuck, but at least attempt it. right? And it's very important that you develop that skill, because there will be questions on our first exam where you need to draw the graphs by hand, and you will not have a graphing calculator on the test. You will not have Desmos on the test, so you need to develop that skill. So what I'm going to do for you here is go ahead and sketch these curves. I'll sketch them here. The constant function 5 is a straight horizontal line. And e to the negative x is a decaying exponential looking like this. X equals 0 is right here, and x equals 3, maybe right here. So the area that I'm looking for is the area between those two curves from 0 to 3, which is this area. And according to the rule above, what we need to do is just integrate the upper function minus the lower function from 0 to 3. And you can see if I were to find the area under f, that would be this rectangle, and then subtract the area under G, that would be this region down here, you will get the area that is between them. But rather than setting it up as two separate integrals, I'm going to jump straight to the upper minus lower thing. So my area here should be the integral from 0 to 3 of my upper function, which is just 5, constant function 5, minus my lower function, which is e to the negative x. Okay, so that's our integral set up and ready to go. Before I calculate the integral, are there any questions about how we got the graph or how we got this integral that we're now going to compute? Everybody remembers the graph of e to the negative x? All right, this green, this blue graph here. So one way to remember what that graph looks like, there are some graphs that we just have to know, right? So y equals e to the x looks like this. Right, this is sort of your standard exponential function, right? Growing exponential. So y equals e to the negative x, multiplying by a negative on the inside flips over the y-axis. So I'm just going to take the graph of e to the x, which is one we should know well, and I'm going to flip it over the y-axis, and that will give me the graph of e to the negative x. I just take this guy and flip it over. This is one of our basic transformation rules from pre-calculus. I do have, let me show you really quickly while I've got our focus on this. If you go to the modules section in Canvas, one of the all-important things here are the basic graphs. Where are they? Oh, I think I put it in my Calc 1 thing. I didn't put it in my Calc 2 thing. So let me add this to your Calc 2 thing. Okay, parent functions for Calc. Open it. All right. So this big mess of things is a Desmos environment where I've just preset all of the parent functions or basic graphs that you need to know. So I'm going to turn off all of them except for the one that we're starting with here. There it is. All right. So here is e to the x. right? And then the transformation rule just says if you want e to the negative x, you'll flip this over horizontally. There it is, right? So this is the graph that we're working with. Let me take this guy and I'll add it to your modules. Tab, one down, one left. There we go. All right. So now when you go into your modules under that review material, there will be a link here to that Desmos environment. And if there's ever a basic graph that you forget, you can take a look at it. I'll tell you this, you need to have these memorized before the test. These graphs, these are fundamental, right? These are things that coming out of pre-calculus we really should know. If you've forgotten one temporarily, that's okay. But if you find yourself having a hard time conjuring these as a general rule, I strongly suggest you make some flashcards and drill them until they stick in your head. Right? Sketch them, draw them by hand, and they will eventually stick in your head. Have a flashcard on one side, just have the name of the function. On the other side, have the graph. When you look at the card on your own paper, try to sketch the graph, then flip over the graph, flip over the card and see if you got it right. Do that with those until they stick in your head. Okay, how do I evaluate this integral? Remember, you can hold the space bar to talk. You can type in the chat.
We have to take or create new bounds first.
If we were going to do a substitution, which we might do for this guy, that would require creating some new bounds. There is a suggestion in chat that a DM, that we separate the integral. And I think that's an okay thing to do here because we're going to kind of use different rules for each. So integral 0 to 3 of 5 dx minus the integral from 0 to 3 of e to the negative x dx. Now down the road, a little later in the semester, I will expect you guys to be able to do this like bam, really fast. But at the moment, I'm okay with taking a second to explore how to do these. This one requires a little bit of thought. This one should be instant, right? So what is an antiderivative for 5? Who has derivative 5? Very good. Yeah, so in the chat there we have the full antiderivative, and that is correct. I'll go ahead and write that down. So the antiderivative for 5 is 5x, and we would evaluate that from 0 to 3. And then the result here after we do everything is going to be plus e to the negative x evaluated from 0 to 3. Now let me explain where this second guy is coming from, because you notice this minus became a plus. Here's a simple rule. The integral or antiderivative of e to the ax dx is always going to be 1 over a times e to the ax. And if we're doing it like this, indefinite integral, we would write a plus c. This comes from a little u sub. I call these micro substitutions. The actual substitution, if you wanted to write it out, would be z equals ax, which means dz would be a times dx. And that statement about differentials can be written as 1 over a dz is equal to dx. All right? So this is the substitution you would make in this integral, because the differential dz is just a times dx. You need to solve that for dx, and you get 1 over a dz. So this integral would become e to the z times 1 over a dz. and the 1 over a pops out. So this is the micro substitution that does the job. And up here, this is the rule. You do want to remember this. All right. The way you remember that is by proving it, right? And this is not a hard thing to prove. So take a minute, write down this integral, make this substitution, and verify that this is what you get. It's not at all hard. What that means is that the integral of e to the negative x dx is going to be 1 over -1 times e to the -1 times x, right? This guy is this guy with a equals -1. So what do we get? Now, if I go to evaluate between bounds, when I plug in the 3, here I'll have 5 times 3 minus 5 times 0. That's plugging in the 3 and the 0, evaluating this first bracket. Plus my second bracket, I'll have e to the -3 minus e to the -0. On a good day, 5 times 0 is 0. What is e to the -0?
One.
Very good. -0 is 0. So e to the -0 is e to the 0, which is 1. So what do I get? I've got 5 times 3, which is 15, plus e to the -3 minus 1, or 14 plus e to the -3. And you could write that e to the -3 as 1 over e cubed if you wanted to. But there's no need to. Either form would be perfectly acceptable. And that's it. That is the area bounded by these curves. You fit the whole example here if you want to take a screenshot. Now is a good time. Any questions on this guy? Good. Yeah. Funny story here. So I'm getting some DMs that make me chuckle a little bit, and it reminds me of a story from my own Calc 2 class. I remember very first day in Calc 2, my professor asked us to integrate, I think it was like e to the 5x or e to the 3x, something like that. He put it up on the board and he started cold calling people. His name was Altai Ozgener, man that I love dearly to this day. And I remember sitting there going, fuck, I don't remember. And it had just been like you guys, it had been Christmas break. And I was very, very nervous. And he cold called like 3 other people. None of them knew it. And he told them all to get out of the classroom. He said, if you don't remember this, you need to leave right now. One of the kids got up and left and never came back. The other 2 stuck around. And eventually he just reminded us how to do it. So don't feel bad, right? At that moment, I didn't remember it either. And now I'm a math professor. Things worked out okay. I just worked hard. I went home and reminded myself how to do this stuff by solving problems. So that's what you need to do if you're not remembering this right now. We need to go back and practice solving some of these problems. There's another good question here in the DMs. Rather than evaluating these separately, could I have evaluated them together? That's a great question, and the answer is yes. This is the same as 5x plus e to the -x evaluated from 0 to 3. Yep. And more generally, if you have a times f of x plus b times g of x, oh, I guess I shouldn't have used a's and b's here. Capital A, capital B, evaluated from little a to little b. The evaluation bracket is linear, meaning this is the same as the constant a times f of x evaluated from a to b plus the constant b times bracket g of x from a to b. So whichever way is easier for you to evaluate, you can do, right? If you've got two chunks like this, you can either think of them like this as a single thing, or you can split them up and evaluate either way. So if you get something like this, you are free to split it up like this. Or if you get something like this, you're free to combine it like this, whatever feels more comfy to you. The sign change. So this minus became a plus. The question in chat, why did we add these? Because the antiderivative for e to the negative x is negative e to the negative x, coming from this rule. So the antiderivative here, if you wanted, you could think of this as a minus and there being a negative here. That's kind of the in-between step. So this would be minus negative e to the negative x from 0 to 3 like that. And then this negative pops out and makes this guy a plus. These are all really good questions, really good comments. I'm glad to see your brains coming back into calculus mode. Anything else like this? Or Amanda, is that satisfactory? Maria? Of
Yes, thank you.
course, very good, very good. Maria, is the thing with the evaluation brackets making sense? Feel comfy? Okay, I'm going to take that as a yes. We do have to move on. So if both of your curves are functions of x and they never intersect, or they don't intersect anywhere over your interval, then you just subtract upper minus lower, integrate from a to b. That gives you the area between them. Two kind of ways this can be complicated. First, maybe those curves intersect at some point. Maybe one is the upper, and then later the other is the upper. Got to know how to deal with that. The other possibility is that maybe one of them isn't a function of x. Maybe it fails the vertical line test. And in that case, we need a completely different approach. So let me address the first complication first. What if the curves swap places? So maybe sometimes f is the upper curve, and other times g is the upper curve. For this picture, I'll put a here, and I'll put b here. Again, we're looking for the area between these curves, which is more or less this area. Ignore this little guy. I'll mark the intersection point here, his x value, as C. If I just asked you for the area between these two curves from A to C, from here to here, you would integrate the purple minus the blue, right? Upper minus lower. And if I asked you just for the area between these curves from C to B, you would integrate the blue minus the purple, upper minus lower again. So if the curves swap places, one of them is the upper for some time, and then the other one is the upper for some other time, then you just need to split it up. The way the book shows this, they say you should integrate the absolute value of f minus g. But nobody does that in practice. In fact, the way you integrate an absolute value function is by splitting it up. So the way to think of this, you would integrate from A to C, the upper minus the lower there, which is f minus g. And then add to that the integral from C to B of the upper minus the lower there, which is G minus F. In other words, if you're given two curves that intersect and swap places, in order to find the area between them, you need to find the x values of those intersection points. You need to find those intersection points and split the integral up there, split the problem up at that intersection point and make it two problems, each of which we know how to solve using the previous technique. Okay. So this adds an extra step. This adds the extra step of finding the intersection points. And the classic problem here is sines and cosines. So let me do that. Let's find the area between f of x equals sine x and g of x equals cos x. Let's do x equals 0 to x equals pi over 2. Again, we need to draw the graphs. All right, so getting good at drawing graphs is huge. If you did not develop that skill in Calc 1, it is late and it needs to be done. So every single time I give you a problem from chapter 6, every single time you need to draw the shit by hand. Sine and cosine are both little waves. Their amplitudes are 1. The period is 2 pi. So I've marked a 2 pi here. I will mark a half period here, which is pi. I will mark pi over 2 here. And I know I'm really just looking from 0 to pi over 2. All the business is going to be over here. But just to help you get back into the swing of drawing these graphs, I'm going to sketch a full period for both. The sine curve starts at his equilibrium point and goes up to a max at a quarter period, back to the equilibrium at a half period, down to a min at 3/4 period, and back to the equilibrium at the full period. So in purple here, I am drawing the function sine x. There it is. That is one period of the sine function. All right, and we know it goes off this way and continues doing more of that stuff, goes off this way and continues doing more of that stuff. Now this is f of x equals sine x in purple. We will use a lot of trigonometry in this class. The cosine curve starts out at his maximum at the top of his amplitude, comes down to his equilibrium at pi over 2, attains a min at a half period, comes back to equilibrium at the 3/4 period, and ends back up at his maximum. So the cosine curve is like this. And he continues doing this stuff, you know. All right, so here are sine and cosine sketched from 0 to 2 pi. We want the area between those two curves from 0 to pi over 2. Before I start setting up the integral, are there any questions about these graphs? All right, practice makes perfect. Again, if you look in the review modules, you come in here, just go to any Paul's online notes page, trig review. You can find links here that will take you to the graphs and you can practice them, right? Cosine, he talks about how to graph these things. Practice this shit. If you don't remember it, you must practice it. Otherwise, you will be boned on the test. So I want the area bounded by these curves from 0 to pi over 2. That means I'm looking for this little sliver and this little sliver. The way we would calculate those is by first finding this intersection point, right? In the first region here, cosine is the upper and sine is the lower. In the second region here, sine is the upper and cosine is the lower. So first we need to find the intersection point. Now these curves intersect infinitely many times. They intersect here, they intersect here, they intersect on this side over here. I'm looking for the first positive value where sine x and cos x are equal to each other, right? So I set the two functions equal to each other. Means I'm setting sine of x equal to cos of x. And there are multiple ways to solve this trigonometric equation. We could encounter more complicated trig equations. And if you are struggling with those, you need to go back to your trig notes and remind yourself how to solve trig equations. This one is not bad. You can get there thinking about your unit circle, or you could divide both sides by cosine and say tan x equals 1. Either one is fine. I think most of us are probably more comfortable thinking about the unit circle in terms of sine and cosine. There is a point in quadrant 1, right? As I rotate up through quadrant 1, there is a point where sine and cosine are equal right here. Root 2 over 2, comma, root 2 over 2 is the point on the unit circle. What is this angle here? The angle where cosine is root 2 over 2 and sine is root 2 over 2, the first positive angle. What is that? Let's see something in chat. Yeah, I have two correct answers. One came as a DM. We've got 45 and pi over 4. 45 degrees is correct. Another little note here. This is a mathematics class, and in mathematics classes, we don't fuck with degrees that much. It's all about radians. Degrees have units. Radians are dimensionless. So you can ask your physics professor about this if you're taking physics. Radians are beautiful because they have no units. They are dimensionless. So we will always use radians in this class. So 45 degrees is a correct answer here, but in radians, that's pi over 4, right? And you notice I labeled all of these on the axis here in radians, not in degrees. We'll always work in radians. So this guy right here, that intersection point is pi over 4. Therefore, in order to find my area, I'll set up two integrals. One integral from 0 to pi over 4 to measure this first area, and another integral from pi over 4 to pi over 2 to measure this area. It turns out that these are actually the same areas, so we could exploit a symmetry argument if we wanted to. I'm going to begin just by setting it up kind of barehanded without using any symmetry. This is the integral from 0 to pi over 4 of the upper function there minus the lower function there, which is cos x minus sine x dx. This is my first little region. My second little region is going to be the integral from pi over 4 to pi over 2. So I write plus integral pi over 4 to pi over 2 of the upper function there minus the lower function there. So that's sine x minus cos x dx. And due to the symmetry of these graphs, I can actually get this as twice the first integral, integral 0 to pi over 4 of cos x minus sine x dx. On exams, you are allowed to use symmetry arguments, and I encourage you to use symmetry arguments. They will save you a lot of time. But you do have to tell me what you're doing. So we can say that the sum of these two integrals is the same as double the first integral by symmetry. If you see the symmetry, exploit it. That's awesome. Do it. If you don't see the symmetry, that's okay. Just go ahead and crunch this out. It'll take a little bit longer, but you'll still get the right answer. All right, we're almost done. This 2 is going to come along for the ride. Now we're ready for our antiderivative. What is an antiderivative for cos x?
Sine x.
Sine x. Yeah, good. Now I need to subtract the antiderivative for sine x. What is the antiderivative or an antiderivative for sine x?
Negative cosine x.
Good. So I'm going to subtract negative cosine x, which means we're going to add cos x here. And then we evaluate from 0 to pi over 4. Any questions about the symmetry argument or the antiderivative? Tyler asked an interesting question. How often can you use symmetry, specifically with trig functions? I want to give you an answer that's not like a cheeky joke, but often. I can't. That's not a question that has like a clear quantitative answer, but surprisingly often, right? Trig functions are periodic, which means their graphs have a lot of symmetry. And then it goes deeper than that. Because the trig functions come from the unit circle, there's even more symmetry inherent beyond the periodicity because of the symmetry of the unit circle. So the answer is surprisingly often. Maybe that's the best answer I can give you there, Tyler. Surprisingly often you can use symmetry. If you're looking at a region bounded by trigonometric functions and it looks like two parts of it might be symmetric, probably they are. And if you really want to find out, do the computation both ways, or do the computation one way by hand, and then do the computation the other way using Wolfram Alpha or something, and check, right? It's a nice thing to explore. But yeah, surprisingly often is probably the best answer I can give there. Okay. So now let's finish this up. If I evaluate this expression at pi over 4, I get the sine of pi over 4. I'll write it out. Plus the cos of pi over 4. And then I need to subtract what we get at 0. And I'm going to require some participation at this stage. Let's start with the zeros on the far right. What is the cosine of 0? We can come back to talk a little more about symmetry in a second, but let's get through this first. So what is the cosine of 0? Very good. The cosine of 0 is +1. Right? The x coordinate, if you rotate 0 radians up right here on the unit circle, the x coordinate is 1. What is the sine of 0? What is the y coordinate at that same point? Excellent, 0. Okay, what is the cosine of pi/4?
Square root of 2/2.
Good, √2/2. And we argued a minute ago that pi/4 is the place where sine and cosine are equal. So the sine of pi/4 is also √2/2. So altogether, what do I get here? I have my 2 out front from the symmetry argument. I have √2/2 plus √2/2 minus 0 plus 1. √2/2 plus √2/2 is 2 √2/2, or just √2. Right? This parentheses, when you add these up, you just get √2. And then minus 0 plus 1, that's just -1. So we get 2 √2 minus 2 for our final answer. And we'll put a period there to denote the end of the thought. So here's the whole computation. If you want to take a screenshot, this is a good spot to do so. Actually, we can get the whole problem in here with the graph and everything and still keep it legible. And we'll do it like this. Okay. So if you want a screenshot, here's a good spot to take one. Now, a question came in as we were finishing up that integral, just a little discussion of the step from here to here again. The logic is this integral measures this area. And this integral measures this area. So specifically, Kim, the first integral measures the first black shaded region, and the second integral measures the second black shaded region. Just looking at the graph, this is really where this is coming from. I'm just looking at the graph. It appears to me that this region and this region are mirror images of each other, meaning they have the same size. So if I want to get this area plus this area, which is what this original integral sets up, since these guys are the same size, they're mirror images of each other, I could compute this one and double it. Or I could compute this one and double it. All right? It's really 2 copies of the same thing. So rather than computing separate antiderivatives with separate bounds, I just take the first one and double it. I like to use 0 as a bound wherever possible because it's nice. And of course, if I can save myself doing a second antiderivative, that's nice as well. Beautiful. Okay, I'm glad. Any other questions or comments on this one? Sean asked a good question. Is it the case that every time something looks symmetric, it actually is symmetric? Yeah, and I'm glad you added that addendum, assuming your graph is drawn well enough. Yes, with the addendum, right? But modulo your graph drawing skills, it is entirely possible that I were to draw a graph poorly, making something that isn't symmetric look symmetric. That is theoretically possible. So be careful with your assumptions. If you're unsure, go ahead and compute it one of the ways, and then use some calculation tool like Wolfram, Photomath, whatever, to do it the other way, and see if you get the same thing. But yeah, most of the time, especially with trig functions. Okay. There is another sense in which these problems can be more complicated. Of course, you can kind of induct on that. It's possible for curves to swap places multiple times, right? Going back and forth. And if you have a problem where you've got like 3 regions and the curves keep swapping places, then you'd have to set up 3 integrals and so on. It's possible that you have multiple boundary curves, right? Instead of just 2 boundary curves, maybe 3 or 4, and you need to look at each little chunk as its own integral, integrating upper minus lower. But beyond all of that, it's also possible that one or both of your curves cannot be expressed as a function of x. So what if one or more curves cannot be written in the form y equals f of x, right? So the classic example here, actually, before I do the example, I'll draw a general picture. And I could have something like this for my first curve. Well, y is not a function of x here. X is a function of y here. And then for my second curve, I might have something like this. And again, y is not a function of x here, but x is a function of y here. In this case, if I want to find the area bounded between these two curves, which would be like this area, I need to set the integral up with respect to the variable y. Basically, turn your head sideways, right? Now there's an upper and a lower, right? If I look at it like this, purple is my upper, green is my lower. Well, that's what's going on. We're going to take the larger output values and subtract the smaller output values from them. In this case, your integral will be set up as a dy integral, which means that your bounds will be y values. And that's the thing that we really need to get into our heads here. So if I want, if I wanted to find the area bounded between these two curves, I would integrate the larger function, and larger outputs here mean larger x values, minus the smaller function, and smaller outputs here means smaller x values. So in other words, you're going to integrate the right function minus the left function. So this would be the integral from y equals a to y equals b. And I'm writing the y equals just to emphasize that a and b here are y values, not x values. I don't care what the x value of this point is. I don't care what the x value of this point is. I need the y values. And then you'd integrate the larger function, which means the right function, which is f, minus the left function. And these are both functions of y, right? Like maybe y squared plus 1 and sine of y or some bullshit like that. So your integral is going to be done dy. You can write out Riemann sums for these things if you want. Your little Riemann rectangle that you would draw in here as a prototype would be a sideways rectangle. And this distance would be the x value here minus the x value here. The x value here would be f of y, because x is f of y. The x value here would be g of y. So your kind of Riemann rectangle height, if you like, would be f of y minus g of y. And then the width of that little Riemann rectangle would be a delta of y. So in the limit, this is what you would get. And the sort of simple way to think of this is the integral from a to b of the right function minus the left function. But you need to express both functions in terms of the variable y. In other words, you need to solve for x. All right, I'll show you a concrete example. Okay, let's look at an example. Just a little bit. Okay, and I'll tell you this guy is x equals y squared minus 1. Right, this is a sideways parabola whose vertex is over here at -1, 0. That is y squared minus 1. One such function. And then let's get a linear function in here. Okay, and this guy is x equals, or let me write it. Yeah, let's do it the other way. That'll be more fun. Let's say this is y equals -x plus 1. Okay, and I want to find the shaded area. We need to look at the picture and ask ourselves whether we're going to do this thing or the first thing. Am I going to do right minus left, dy, or upper minus lower, dx? The way to figure that out is to ask yourself, is there an upper and a lower? Is there a right and a left? If I'm looking over here, the purple is the upper and the green is the lower. But if I'm looking over here, the green is both the upper and the lower. That's weird. On the other hand, if I think right and left, the purple is always to the right of the green, no matter where I look. So the purple is always the right, the green is always the left. That tells me I should set it up this way. There is a well-defined right function and a well-defined left function. There is not a well-defined upper function and lower function. So we're going to set this up using the dy integral, the right minus left scheme. In order to do that, I need the intersection points. So we're going to set this up as a dy integral because there is no well-defined upper and lower, but there are well-defined right and left functions. So that's how you decide, right? And some of the problems in your homework say decide whether to integrate with respect to y or respect to x. This is how you do it. So you sketch the region and then ask yourself, is there an upper curve and a lower curve? If the answer to that is no, you ask yourself, is there a right curve and a left curve? One of those questions, the answer will be yes. Here, there is not an upper and lower throughout this region, but there is a right and a left consistent throughout this region. So we will use the right minus left thing. Next, intersection points. These curves don't swap places, but the region is determined by the intersection points, right? So if I want to find the y value that is the smallest y value in my region, that's down here. And the y value that is the largest y value in my region is the one up here. So if I want to integrate from the small, look down, look here. A, the lower bound here, this is the smallest y value in the region. And B up here, this is the largest y value in the region. That's how you determine what to use for your bounds. And in this particular problem, the smallest y value in the region and the largest y value in the region are both intersection points. So in order to find those bounds for my integral, I need to find the intersection points. Like before, we find those by setting the two curves equal to each other. But in the form that these are in, I cannot set them equal to each other. This one is solved for x. This one is solved for y. So if I'm going to set them equal to each other, I need them either both solved for y or both solved for x. Which should I do here? Should I solve this for y and then set the result equal to this? Or should I solve this for x and then set the result equal to this? Yeah, Fabrice is correct. We should solve the purple equation for x. First off, it's much easier, right? If I try to solve this for y, I'm going to end up with a square root and a plus and minus, and it's just not pretty. This is very easy to solve for x. Secondly, I'm going to integrate right minus left. That means I need to get both my right and my left in this form, x equals some function of y, x equals some function of y. So I needed to solve this for x anyway. So let me begin here. I can add x to both sides, and then I get x plus y equals 1. And then I can subtract y from both sides, and I get x equals 1 minus y. So the purple curve can be re-expressed as x equals 1 minus y. And then to find my intersection points, I will set 1 minus y equal to y squared minus 1. Set the two functions equal to each other. Now just some baby algebra. Make the left-hand side 0 by adding y to both sides and subtracting 1 from both sides. That gives me y squared plus y minus 2. Now I need to factor this quadratic, which means I need two numbers whose product is -2 and whose sum is +1. Two such numbers there are +2 and -1. So this is going to factor as y plus 2 times y minus 1. So the two solutions that I get out are y equals -2 and y equals +1. Those are your intersection points. This guy here is -2. This guy here is +1. All right, the y values. Don't care about the x values. I could not care less what the x value is here. Now we're ready to set up our integral. That will be the integral from -2 to +1 of my right function minus my left function, both of them as functions of y. So the purple curve can be written as x equals 1 minus y. So that is just 1 minus y. And now I need to subtract my left function, which is y squared minus 1. And the integral is being done dy. Any questions on how I arrived at this integral? Okay. So I'll combine my like terms, just clean up the integrand and write it in a nice format. I'll have a -y squared minus y, and then 1 minus -1 is +2. Yeah, that's correct. We need to find the intersection points before we can write down the integral, because the intersection points are what tell us the bounds. So the kind of order here is draw the picture, shade the region, decide whether to integrate with respect to x or with respect to y. That's the, am I going to do right, left, or am I going to do up, down? After you've done all of that, then you find your intersection points to determine your bounds and write down the integral. Okay. So in this last step, all I did was distribute this negative here, making this negative y squared and plus 1, and then I combined my like terms. So I had a negative y squared goes here. I had a negative y already, that's here. And then I had a positive 1 and minus 1 makes plus 1. 1 plus 1 is 2. So just distributing the negative and combining like terms gets me here. And if it's okay with you, I'm going to pull this over here to continue. I need an antiderivative. Each of these will follow from the power rule. So the antiderivative for negative y squared is negative 1/3 y cubed. Add 1 to the power, divide by the new power. Negative comes along for the ride. Antiderivative for negative y is negative 1/2 y squared, or negative y squared over 2, if you prefer to write it that way. And the antiderivative for plus 2, remember we're integrating dy, so this isn't going to be 2x, it's 2y. So be mindful of that. It is possible to make mistakes there. If I plug in the upper bound, 1, I'll get negative 1/3 times 1 cubed minus 1/2 times 1 squared plus 2 times 1. That's negative 1/3 minus 1/2 plus 2. And then I'm going to subtract off what I get when I plug in negative 2. Negative 2 cubed is negative 8. Negative 1/3 times negative 8 is positive 8/3. Plugging the negative 2 in here gives me positive 8/3. If I plug the negative 2 in here, I've got negative 2 squared is positive 4. Positive 4 times negative 1/2 is negative 2. So minus 2 there. And then finally, plugging the negative 2 into the 2y, I just get 2 times negative 2 is negative 4. We can clean this up quite a bit. Let's put the integer stuff together. I've got a positive 2 minus negative 2 is another positive 2. So the 2's here will add up to 4. And then minus 4 is going to be 0. So everything just comes from the fractions. I've got minus 1/3, minus 1/2, minus 8/3. So did I integrate backwards? Minus 1. Okay, we're okay. So what do we have all together? I've got, I'll just write it out, minus 1/3, minus 1/2, plus 2, minus 8/3, plus 2, oh, plus 4, yeah. Okay. So what do I have here? I've got 2 plus 2 is 4, plus another 4 is 8. That's just the integers. I previously said the integers sum to 0. I got a sign wrong now, I'm sorry. Then we'll have minus 1/3, minus 1/2, minus 8/3. The step to go from here to here is just plugging in 1 and then subtracting what you get when you plug in negative 2. So this piece, I'm not going to go back through those details, but you can annotate. This came from plugging y equals 1, and this came from plugging y equals negative 2. Okay, and then to combine these ratios, the negative 1/3 and the minus 8/3, I can combine those right away. negative 1/3 minus 8/3 is negative 9/3. And 9/3 is 3. Eight minus 3 is 5. So this is 5 minus 1/2. And 5 as a ratio over 2 is 10. So this is 10 halves minus 1/2, which is 9 halves. And that's your final answer. Oh, the antiderivative comes from the power rule. So yeah, that I don't mind going back over really quickly. The power rule says that if you're integrating, I'll write it in terms of x to the n dx, this will be 1 over n plus 1 times x to the n plus 1 plus c. Right, since I'm writing it as an indefinite integral there. So, for example, the integral of negative y squared dy, the negative pops out, and you have integral y squared dy, should be negative, and then n is 2 here, so n plus 1 is 3, so the 1 over n plus 1 is 1/3, like this, plus c, and so on. So yeah, each of those antiderivatives comes from the power rule. You add 1 to the power and divide by the new power. And then the constants, like these negatives, just come along for the ride. If you're wondering, there is both in the review section of the modules and the textbook a collection of integrals that you should be comfy with. It's in chapter 5, I think, here. Right here. So in the textbook on page 403, if you look here, these are the basic rules for integration that you need to know. You need to know these cold. These should all be things that come to you immediately. And the power rule is right here. Now this works as long as n's not -1. If you're integrating x to the -1, that's the integral of 1 over x, which we know is the natural log function. But this works for all other powers: integer, non-integer, rational, irrational, positive, negative, whatever. So again, that was page 403 in the textbook. If you want to take a screen cap of this, that's not a bad idea. When my wife took Calc 2, we made flashcards for each of these. There's a bigger version of this in 7.5. It has a few things that we haven't cooked up yet, but we'll cook up soon. Cool. All right. So you can integrate upper minus lower. You can integrate right minus left. And if the curves swap place, you swap, you split up the integral. Areas between curves, easy stuff. In the last few minutes before I let you go, and I think we are approaching the end of class now, I want to talk about average value. This is an important concept in statistics, specifically if you're talking about calculating probabilities where you're given some sort of probability mass function. You need to find the area underneath that. If anyone's taken STA 2023, you know that if you have a bell curve, like a normal distribution, and you want to find a probability that some random variable takes a value between this and this, you're actually looking for the area under that curve. That notion from statistics is very important here. It comes from this. So I'll begin by saying recall. To find the average of n numbers, call them y1, y2, y3, out to yn. So each one of these things is just a number. I want to average them. What we do we sum the values and divide by the number of numbers. So this would be y1 plus y2 plus y3 plus, you add them all up out to yn, and you divide by the number of numbers, which is n. And you could call this the average of all the y's, yav, like this. This is how you find the average or mean of a set of numbers. You just add them all up and divide by the number of things. What if, period, question. What if I want to find the average of all the outputs of a function, call it f of x, as x runs from A to B. Right? In other words, I want to find the average of all the y values on the graph. That is, find the average, or mean, it's called, of all the y values on the graph over the interval AB. Well, let's draw a picture. Here's my function f. Maybe A is here, maybe B is here. What I want to do is average all these y values. Now, I'm not putting a point at every single one because that's precisely the challenge. There's infinitely many. I mean, if f is a constant function, then there's just one y value, right? But if f is like a normal curve, a curve that isn't constant, you know, moves around some, you're going to have infinitely many different y values here. So I can't just add them all up and divide by the number of y values. For one thing, adding them all up would mean adding infinitely many things. That's a tricky biscuit. We'll talk about that later in the semester, but certainly not right now. And then you'd have to divide by infinity, which is also quite tricky. But we can start by chopping this x interval up into a bunch of pieces. And I can say, well, you know, if I chop it up into finitely many pieces, then I can certainly average those. Okay, if you have to go, you have to go. I'll post the recording here, but you do need this for your homework. So if you're leaving, let me just tell you the result here. The result is that the average value is going to be 1 over b minus a, the length of the interval, times the integral from a to b of f of x dx. So you integrate and then divide by the length of the interval. That's the result. Okay, if you gotta go, you gotta go. I get it. Here's the last thing you need for your homework. Why is this the case? Well, if we partition the interval into n equal length subintervals with endpoints xi equals a plus I times delta x, where delta x is the width of one of those subintervals, b minus a over n, then we can approximate, we can sum the outputs of f at the xi's. So this is like a, which would be x0, x1, x2, x3, and so on until you get to b, which would be xn. Now I have finitely many things that I'm trying to average. I'm trying to average this y value with this y value and this y value and this y value, just finitely many, which means I can use the formula above. So f av might not be exactly equal to, but should be approximately equal to the sum of all of these y values, which we would write as capital sigma I from 1 to n f of xi. Or at least this would be the sum, I should say, and then you need to divide by n, right? Over, I'll write it in the notation we were using it before, over n. So compare this to this, right? This, by the way, can be written, if you're not familiar with the sigma notation, you should be from Cup 1, but this would be the sum from I equals 1 to n of yi all divided by n. This big addition problem can be written compactly using this notation. Now this object I can clean up quite a bit. This is the same as sigma I from 1 to n f of xi times 1 over n. Right? Dividing by n is the same as multiplying by 1 over n. Now I can get sneaky and multiply by b minus a over b minus a. The reason we're going to do that is because of your Riemann sum formula for the definition of the integral. Your delta x in your Riemann sum is b minus a over n. So if I group this with this and I pull this out front, I get the following: 1 over b minus a, that's this downstairs b minus a being pulled all the way out front, times sigma I from 1 to n f of xi times b minus a over n. And you may or may not recognize this at this stage. If I rewrite b minus a over n as delta x, hopefully you will recognize it. This is the formula for the Riemann sum that represents the definite integral. This is 1 over b minus a times sigma I from 1 to n f of xi times delta x. Now, we started saying the average value is approximately this sum divided by n, because this sum doesn't have all the values of the function, just the values at the points x1, x2, x3, x4. But if I send n to infinity, that means I send the number of sample points here to infinity, then I really do get all the y values on that curve, right? There's infinitely many y values there, one for each of the x values in the interval a, b. I've chosen to, instead of looking at every x value in there, just look at finitely many of them by partitioning that interval. This sum is the sum of those finitely many y values, but now I'm going to send n to infinity, so I'll get all the y values. Now, as n goes to infinity, f av is equal to the limit as n goes to infinity of this expression. The approximately equal to becomes exactly equal to, because now I'm actually looking at infinitely many sample points. I'm going to get them all. And then you have your sigma I from 1 to n, f of xi times delta x, which is 1 over b minus a times this object is Rn, your right endpoint Riemann sum. So you have 1 over b minus a times the limit as n goes to infinity of Rn, your right endpoint Riemann sum. And as you send n to infinity in your Riemann sum, you get the integral from a to b of f of x dx by definition. Go look back at section 5.2 where you defined the definite integral. It is the limit as n goes to infinity of the Riemann sum. So that's it. That's the proof. So if you want to average all the outputs of a function, you can integrate that function and then divide by the length of the interval, which is what we said at the start in the box. Just wanted to show you where it comes from. There are some cool geometric interpretations of this, which we don't have time to get into now because I've got to get moving to another class. So I'm going to go ahead and stop here. On Monday, I'll show you a way to interpret this formula geometrically. It's quite cool. And there's a connection to the mean value theorem, which we'll explore a little bit before moving on to talking about volumes. So at the start of next week, we're going to talk about volumes. Be mindful that the homework, which is open now, is due at the start of class on Monday. So please don't put that off. It's not due at midnight on Monday. It's due at the start of class. So I'll be working on that stuff. If you need to talk to me, I've got office hours. Otherwise, I'll see you guys next time. Take care.